In this video, I want to show you several examples of how to use the thermochemical equation in order to make various calculations. So in this one, let's imagine that we are told that we have this many grams of H2S, and we are asked to find how many kilojoules will either be released or absorbed when this amount of H2S reacts with excess oxygen. So the first step, as it has been in many cases, is to figure out how many moles of H2S this will be equal to. So sulfur is 32, we can just use 32, and hydrogen is 2 more, so that's 34 grams. And here is what is a little different. For every 2 moles of H2S, and now we're going to use the thermochemical part of the equation. So the question is, how much is released? So I'll explain more about what that word means in just a second and how we interpret that in terms of the signs that are involved. But for the moment, I'm just going to put in this amount. And we see that the grams there will cancel the grams, and moles will cancel moles. And to 3 significant figures, that's going to be 264 kilojoules. So now the question is this amount released or is it absorbed? So if we go back, I'll change colors here so that you can see, and if we go back and we look at the sign here is negative, and a negative sign means the reaction is exothermic, and when you have an exothermic reaction, that means heat is released. So when you refer to the amount of heat, you basically use the absolute value. You don't use a negative or positive. The negative or positive comes in with the word that you use to describe it. So if you are saying that heat is released, then that's negative, and if you're saying it's absorbed, it's positive. So that can sometimes be a little bit confusing. So I'm going to go ahead and just add the word here, released. In this example, we'll take a look at the problem from a different perspective. So let's say that the problem was something like this, that we were being asked how many grams of methane would it take to produce 330 kilojoules. Well, we know from the thermochemical equation that 890 kilojoules are produced for every 1 mole of methane, and we know that a mole of methane is 16 grams. So we can multiply that. So we're going to multiply 330 times 16 divided by 890. And what that tells us is, to 3 significant figures, it's going to take 5.93 grams of methane to produce that many kilojoules. So you can see that this is really just the reverse of the problem that we looked at before. So to kind of summarize where we are at the moment, we can figure out what the delta H for a reaction is by taking, I'll mark it up here, taking the amount of energy it would take to break those bonds and subtracting from that the amount of energy not that it would take, but would be released when you form these bonds over here. And that is where we get this number. This is the 890. What that really is, or what that provides us with, is a conversion factor. So now we can use that as a conversion factor, just like we've used any number of things as a conversion factor. So this is just another way to extend our idea of stoichiometry to include heat as well as grams, moles, liters of gas, whatever it is that we've talked about.